This is Guillermo Salinas from Airbus Crisa, and I'm a flight hardware designer for this project for GIESEPP MP. So today I'm going to show you a short tutorial about magnetics design for space applications and why it has been so important for the project. So first of all, what are the magnetic components? So basically they are components that store and transfer energy, and they can be found in many different circuits like power converters, filters, and current transformers for current measurement. So they can be seen here in these schematics. And regarding space applications, we can find them in power conditioning and distribution units, PCDUs, or in propulsion power units, like this one for this project, GIESEPP MP, and for many others, like power supplies for actuators. For example, this one on the image on the right is a unit for launchers. And here we can see how these magnetics look like. So which are the key factors in this project, in GIESEPP MP? So we started from an initial power density of 0.25 watts per cube centimeter. This is the delivered power per unit volume of equipment. And the main goal was to achieve a 30% reduction of the mass, volume, and cost. So how can we do this? From the beginning, we realized that the magnetic components are really bulky, and they occupy most of the space of our converters. For example, on this picture on the bottom, you can see how bulky they are. And they represent a bottleneck on the optimization of our equipment. One of the things that we can do to reduce their size is increasing their frequency. So by doing so, we reduce the size, but as a counter effect, we have heat dissipation. So the more we decrease their size, the more problematic it is, the heat dissipation, or we also call it power losses. So will we be able to make that reduction of the 30% of the mass and volume in GIESEPP MP? We'll see at the end of the presentation. I will reveal it. So let's start our journey about the magnetic components. First of all, how do we classify them? So we can classify them depending on the winding type. They can be made out of foil, as you can see here. This is flat foil. They can be round solid conductors. The winding can also be embedded in the PCBs. They are called planar magnetics. Or we can have these lead wires, which is basically a bundle of multiple conductors which are embedded in this cylinder, and they would look like this. In this particular case, for GIESEPP MP, so we have used foil and planar magnetics in order to achieve the requested solution. Another classification that we can do on magnetic components is that they can be grouped in inductors and transformers. This is a very basic classification. So inductors are used for stored energy, and transformers are used for transferring energy. And in GIESEPP MP, we need solutions for both of them, both inductors and transformers. One main difference between them is that the inductors, most of them have an air gap, which you can see here. So the energy stores mainly in that area. It's a separation between the two ferromagnetic parts of the core. And in the transformers, the energy is more homogeneously distributed along the ferromagnetic core. And you can see also that the transformers have multiple windings, whereas inductors have only one winding. It's important to notice that all magnetic components have a core made out of ferromagnetic material, and as such, their inductance depends on this material that is used and the geometry, the shape of this core. And the winding is also important and plays a role in the inductance that is achieved in these components. This would be the winding for this planar transformer, or in this representation, these are the windings, which are wound around the core. So the first thing that we should really take into account when we are designing magnetic components are the core losses. So if you remember, we said that in order to reduce the size of these components, we want to increase the frequency. But the higher the frequency it is, we have a bigger problem with heat dissipation, with higher power losses. In the case of the losses that correspond to the ferromagnetic material, they can be grouped in these four. There are different mechanics that create these core losses, but the two main ones are the hysteretic losses and the current losses, and both are depending on the frequency. The hysteresis losses depend on the pH curves of the material, of the ferromagnetic material, while the eddy currents are induced in the core, producing therefore some heat dissipation or inefficiency in the component. There are two other types of core losses, which are relaxation losses and DC bias core losses, just for you to know, although in these applications were almost negligible. So this is why it was really important to select our core materials for each of the magnetics that we use in the PPU. The next type of winding losses, of power losses in the magnetic components are winding losses, and they can be grouped in DC and AC. So the DC is what most of you know, which is the Joule heating. Basically, it depends on the DC resistance of the wire and the current that is flowing through it. And now the AC losses depend on the frequency. So again, as we said before, we need to increase the frequency. Therefore, the higher the frequency, the worse power losses we have in these components. So the AC losses can be classified in skin effect, conductor proximity effect, and gap proximity effect. And it is really important to estimate them in order to get the most optimum solution for your magnetics. So let's go a bit into detail in these three. The first one is the skin effect. It is due to the effect of having a high frequency current flowing through our conductors. So in DC, we have a homogeneous distribution of the current through the conductor. Whereas when we increase the frequency, for example, to let's say 500 kilohertz, the current tends to be concentrated only on the outer shell of the conductor. And this region is called skin depth. So the 90% of the current is flowing through this small area of the conductor. The rest of the conductor is basically useless and just creates heat dissipation. So what we need to do in order to reduce this effect is using smaller diameter wires in order to carry that current at that frequency without any trouble. And remember, this effect is worse with the higher frequency. A similar effect is the gap proximity effect. So in inductors, if you remember, some of them, they have an air gap between the two ferromagnetic materials, between the two parts of the core. And this gap, which is basically air or space, vacuum, has this effect of storing energy. As a consequence, when we increase the frequency of our current flowing through the conductors, it tends to be concentrated in the outer shell of the conductor. So basically on these red parts is where the most current density is flowing. Whereas in the blue part, we have almost zero current, which is, again, just producing a heat dissipation problem in these conductors that are close to the air gap. Whereas in DC, we don't have this problem. We see that in DC, the current is homogeneously distributed. Again, this effect depends on frequency. And the last of them, of the winding losses that we can have, is the proximity effect, but in this time, due to the current that is flowing through adjacent conductors. So again, the effect is the same, is that the current tends to be concentrated just on a small part of the conductor, and the higher the frequency it is, the worse the situation, leading us again to heat dissipation. So if we want to reduce the size of our magnetics, we really need to be careful about how do we distribute our wires in order to minimize this effect. So how can we minimize this proximity effect? For example, for transformers, when what we can do is interwind the primary and the secondary windings. So in these pictures here, we have the primary windings depicted in blue and the secondary in red. So primary carries current, which is flowing towards me, out of the screen. And in the secondary winding, the current is flowing towards the screen, so inside the screen, right? So if we don't do anything, what happens at the high frequency is that the current density of adjacent conductors with the same direction becomes even negative. It goes in the opposite direction that we want. And as a consequence, we have higher losses in this conductor. And you see here that in the layer that is between the primary and secondary, we have a very high, very negative magnetic field. And again, it creates more losses. So what we can do by interleaving is put in the primary winding as a sandwich between the secondary winding between the two primaries. And what we can achieve that is that we have a more homogeneous distribution of our current and lower values of the magnetic field, leading to a reduced amount of power losses. So it would be really helpful to be able to use this interleaving in order to reduce the losses and therefore their size. But there are some limitations to this. So there are some standards, mainly the ECSS for Europe, that we have to meet in order to ensure that we will have enough robustness and reliability in space conditions. So this one in particular, which is referred to the restrictions or specifications of PCB design, are applicable in the case of the planar transformers, because as I said before, they are made out of, their windings are made out of PCB. They are embedded in the main PCB. For example, in this picture on the right, we have that layers 1 and 4 are primary winding and layers 2 and 3 are secondary winding. But if we go to this standard and we check which are the clearances that we have to keep in the XY planes or also in the vertical axis, we see that it goes into conflict between the interleaving technique. So most likely we will not be able to have this interleaving in the best level as we wished. And of course, this affected the design of our planar transformers in GIESEPP MP. Another rule that we have to meet is the derating standard, also from the ECSS. So this one in particular is very useful to ensure a low rate failure rate of our components, and again to ensure reliability and robustness during the whole lifetime of our mission. So when we are designing the magnetic component for a ground application, we just take care of the temperature dependence and the tolerances of the manufacturers and so on. But when we are designing for space, we have to meet these ratings in order to ensure enough quality. And in particular, for magnetic components, we have to be careful about the maximum operating voltage and the hot spot temperature. So basically, we need to add additional margins to our design in order to make it reliable. Last but not least, from the ECSS, are these two regarding materials and outgassing. So these standards define which are the materials that can be used and in which conditions. So if you remember, we are talking about the magnetics that are made out of a core and a winding, which has some insulation. We can have an encapsulation, a potting material in order to add insulation. We have PCB with different materials as well. So of course, all these materials need to meet these standards. And as a consequence, we cannot choose freely. And there are some limitations on which materials we can use for space conditions. Finally, there is another standard, which is called ESCC. It's not the ECSS. And these are applicable to all component families, and of course, magnetics included. And they defined which are the tests, the control that we need to have in the production lines, screening, and the qualification testing in order to ensure the proper performances on this type of components in space conditions. So this affects, of course, the mounting methods that we use, and we need to make sure that they survive and they have proper performances in vacuum conditions and with certain temperature cycles, among many other specifications. And finally, I just wanted to mention that another tool when you are designing a magnetic component is the use of finite element analysis simulations. So here in GIESEPP MP, we use them all. We use these simulations for all the different physics that we can find in these magnetic components, which is the electromagnetic type, electrostatic, and thermal. So with this type of simulations, when you have bidimensional or even three-dimensional effects, you can estimate very accurately how much power losses, how much dissipation you have in your component. You can characterize its impedance, its parasitic capacitance, or even checking how much temperature it reaches during operation. And this is really important when you are designing, because you want that result before actually manufacturing these components. So that's why they are very useful, and we use them, of course, in GIESEPP. So as I promised, now I will reveal the result if we did achieve or not the goal of reducing the mass and volume, or what is the same, to increase the power density of our unit. And surprise, we made it. We made it, and we have achieved a power density of 1 watt per cube centimeter. And this was all thanks to putting some special focus on the magnetic components design, as we have seen during the presentation. It's one big point that we should take into account, but of course, it's not the only one. So thank you very much, and thanks for your attention. If there are any questions later, I will be glad to answer. Thank you.